Hello, my name is Jolene Rhodes, and today we're going to talk about volumes of solids of revolution using disks and washers. I'm going to start out with a general picture and how to find the volume, and then do some specific examples. In these problems, we start with a region such as the one shown. Then we take this region, and what we do is we are going to rotate it around an axis. In this case, I'm going to rotate this region about the x-axis. If we rotate this region about the x-axis, that's like imagining the x-axis being kind of a pivot, and that whole region is going to spin around, which will give you a volume of solid of revolution. So what we're going to do is we're going to have a similar picture on the other side of this, and we'll get a picture that looks like this one, where this is a three-dimensional object. It's rounded. Okay, so let's see if we can't make this look a little rounded. It's a rounded object. Looks a bit like a maybe a trophy cup sideways. Anyway, what we're looking for is we want to find the volume of this solid of revolution. Now, the idea with this is very similar to the idea of Riemann sums. What we're going to do is find the volume of a small piece and then use an integral to add up the volume of all of those small pieces. So, for example, if we just take a small slice of this, similar to what we did with Riemann sums with rectangles, and we just look at that small slice and we look at how that rotates around the axis, what we'll end up with is a region. We'll end up with a picture that looks sort of like this one. Now, that is a cylinder. So let's take that cylinder and let's look at our cylinder over here for a minute. And let's recall that the volume, so what we have is a cylinder that looks like that when it's sideways. And what we want to recall is that the volume of a cylinder is equal to pi r squared h. It's basically the area of the circular region times the height of the cylinder. So the volume of a cylinder is pi r squared h. Now in our picture, our radius then is the radius of this circle. So this is our radius. Our height is this side right here. And that's the volume of that one small cylinder. Now if we go back to our picture and we actually look at that cylinder in our picture, what you should see is the radius then of this cylinder, and depending on where we make a cylinder, if I put it over here and I used this piece instead, my cylinders are all different, have all different radii, and they are based on our function value. So in our case, the radius, in this case, the radius is just equal to f of x. The height of the cylinder, what we normally think of as height of the cylinder, is this little section right here, and that's our change in x. So going back again to that Riemann sum discussion, that was basically what we looked at as either delta x or dx in the final integral. So what we have when we take this volume of the cylinder, and what we want to do is add up all of the cylinders, our formula that we're going to need in order to find the volume of a solid of revolution is we're going to integrate, and we're going to integrate from a to b, okay, from whatever x value we're starting at to whatever x value we're ending at. We're going to have pi, our radius, and again, if you look at the picture above, the radius is your function value squared, and then the height, which is the change in x. So our formula for volumes of solids of revolution using disks is going to be pi times our function squared, and the integral from a to b. So let's go ahead and look at a couple of examples. Okay, so for our first example, let's use the region that's bounded by y equal to the square root of x, y equal to 0, which is the x-axis, and the line at x equal to 4. So what we have is I've got this region drawn, and what I want to do is rotate this about the x-axis. So what we'll get is a region, a solid, a revolution, that looks a lot like this one. Okay, so what we'll have is we'll have this solid of revolution. It's going to look like this. And if we look at a representative piece of this, what we'll have is we're going to just kind of take a slice out of this. We'll get a some cylinders. Here's a representative cylinder that's in here. And what we'll get then is what we want to do is add up the volumes of all the cylinders that we see. And so what we're going to do for this particular problem is we're going to integrate our x values. We are going to integrate with respect to x. Our x values range from 0 to 4. We're going to have a pi. I'm going to put my pi in front of my integral because it is a constant, and we can do that. Going to need the function value squared. Now remember, our f of x in this problem, or our y value in this problem, is the square root of x. So I'm going to want the square root of x quantity squared, and we're integrating with respect to x. So if I integrate this, I'm just going to have pi. We'll get the integral from 0 to 4. The square root of x squared is just x dx. If we integrate x, that's x squared divided by 2. We're going to evaluate that from 0 to 4. If I substitute in a 4, we're going to get 4 squared, which is 16, divided by 2, which is 8. So we'll get 8 pi minus, when we plug in 0, we're going to get 0. So our final answer to our volume of this solid of revolution is just going to be 8 pi. And that problem is done. Now let's look at a second example. Okay, so let's use as our example y equal to x squared, y equal to 0, x equal to 1. As you can see, this region, so we've got the x-axis, got the line at x equal to 1, we've got the function y equal to x squared. We're going to rotate that about the x-axis. So what we're going to get is a picture that looks similar to this one. Okay, so we'll have our picture. Here's our region. Here's our object that we're going to find the volume of. And again, in this case then, what we want to do is we're going to have pi. We're going to integrate along the x-axis. Again, if you look at this, we've got all of these little cylinders that we're adding up along there. So they start back at 0. Our starting value of x is 0, ending value is at 1. We're going to get our function, the radius of each of those, which is given by x squared, integrating with respect to x. So what we really have is pi. We're going to integrate from 0 to 1, x to the 4th power. If we integrate x to the 4th power, that's x to the 5th divided by 5. We're integrating from 0 to 1. If I plug in 1 to that, we're going to get 1/5 pi. And if we plug in 0, we get 0. So our volume of that particular example is 1/5 pi. Units cubed, whatever our units might be. So if we actually have units on there, remember volumes are in cubic units. Okay, let's look at another example. Okay, this time let's use that same function y equal to x squared. We're going to use, so y equal to x squared. We want x equal to 0, which is the y-axis, and a line up at y equal to 8. So let's put this up here at y equal to 8. This time we're going to spin this around the y-axis instead. So I'm going to get a region that looks, or solid, that looks like this. And so what we've got is our solid this time is actually going and basically stacking. If you picture these as little discs that are going along the axis, they are stacking up along that y-axis. So we're stacking them vertically versus horizontally along the x-axis. So when you picture stacking these discs that we have in this picture, what we want to do then, by doing this, what this does is this makes our integral not in terms of x's, but in terms of y's. So the only thing that changes to this problem, we're going to do the same kind of thing, except that our entire integral needs to be in terms of y's, because these discs are stacking along the y-axis. Now what that means then is we're still going to use that same formula, except we're going to want to use a pi. We're now going to use our function in terms of y here. So now if you look at our picture, again our discs are stacking in the y direction from 0 to 8, so that does not cause a problem. Again, we're going to integrate with respect to y. I am going to want my function squared. But if you look, what we're given is y is actually equal to x squared. I don't want my function in terms of x's in my integral. I need to be in terms of y. So what we need to do is solve this equation for x. If y is equal to x squared, if I take the square root of both sides, what I get is actually x is equal to y squared. Sorry, that's not what I meant. Square root of y is equal to x. So y equal to x squared. If we take the square root of both sides, we get the square root of y equal to x. So in here, our function now in terms of y is actually the square root of y. And then we would continue this integral the same way we did any other integral. So we're going to integrate from 0 to 8. The square root of y squared, because remember it is squared in the formula from that volume of a cylinder, this is just going to be the integral of y dy. That's pi. Integral of y is y squared divided by 2. We're going to integrate this from 0 to 8. If we substitute 8 in, we're going to get pi times 8 squared over 2 minus 0 if we plug in the bottom limit of integration. And so 8 squared is 64, divided by 2 is 32. So what we're going to get as a final answer is 32 pi. Okay, now what I want to do now is all of these have been solid discs. There's not been any holes in them. They've been just circular discs stacked along an axis. Let's look at another example where this is not as true. Okay, let's go back and use the first region we had from our first example, which was y equal to the square root of x, y equal to 0, and x equal to 4. But this time, instead of spinning this and rotating this around the x-axis, let's rotate it about the y-axis. Now, if we rotate that region about the y-axis, what we're going to get is a region that looks like this one, where what we have is, if we look at a sample disk in here, what we actually have is not a solid disk. We have a disk with a hole in the middle, otherwise known as a washer. Now, with this washer, if you look at this, what we did originally was we found the volume of each of these disks and then we added them together. Well, what we really want to do with washers then is do the same thing, but we want to find this volume of the washer. Now, if we want to find the volume of a washer, what we really need is the volume of that outer disc that has this radius right here, and then we're going to subtract off the volume of the smaller disc whose radius is just right in this little middle section. So what we want is we've got two radii in this case, the radius of the big disc and then the radius of the hole that's in the center of this washer. So if we look at that, what we really want to do, if the thought process is we're still going to do that, use that formula with pi r squared h, but what we're going to have is pi. What we want is we want to find, again, the volume of the outer one. So what we want is the outer radius, in this case, squared. That's that volume of that disc on the outside. Oops, I think this one's in the y direction, so let's put this as dy. We want to go from, say, a to b, whatever our a to b is, and then we're going to subtract off the volume of the inner one, which is pi. Still, we're going to go still A to B. That's the, these are going to stack in the y direction, and what we want to do is subtract off that inner radius squared. And again, this integral is going to be in terms of y. In this particular picture, we are rotating about the y-axis. Our integral is going to be in terms of y. Now, if we look at this picture, in this particular example, then that's going to give us a pi. We're integrating. Think about these disks. The smallest one is down here at 0, and the uppermost one is up here at a y value of what? Well, if we look right here, at this point, that had an x value of 4, and when x is 4, y is the square root of 4, so y is 2. So we are going to, these stack from 0 to 2. Our outer radius, well, what is our outer radius if we look at this? It doesn't actually matter which of these washers we choose. The outer radius is always this line that's out here at 4. So our outer radius is 4 squared dy minus pi. Again, we're going to go from 0 to 2. The inner radius. Now, what is the inner radius in this particular problem? Again, I'm going to want to square it. But let's look and remember that our inner radius then of each of these, here's this one. If I put one in the middle here, see if I can fit another one in. If I put another one in here, here's the outer radius at 4, here's the inner radius right here. And so if you notice, these inner radii are all given by this function, which was the function y equal to the square root of x. Now again, remember we want to integrate this with respect to y, so that means what we actually need is a function in terms of y. So as y is equal to the square root of x, the other way to look at this is x is equal to y squared if we square both sides of our equation. So our inner radius here is y squared. Now if we look at this, you can actually do both of these integrals at the same time. They have the same limits. We're going to integrate from 0 to 2, 4 squared, which is 16, minus y squared squared, which is y to the 4th, and this is all, we're integrating with respect to y, and both of those were multiplied by a pi, so we can put that in front of our integral. And so what we're integrating then is pi, the integral from 0 to 2 of 16 minus y to the 4th. That's going to give me pi. We're going to integrate each of these. Integral of 16 is 16y. Integral of y to the 4th is 1/5 y to the 5th. And I want to evaluate this from 0 to 2. If we plug in 2, we're going to get pi here. 2 times 16 is 32. Minus 2 to the 5th is 32. So I'm going to get 32 fifths. Minus, when we plug in 0, we get 0. So we'll have a final answer here of, which is 128 fifths pi. Okay, so washers, what we need to do is we're going to do the outer radius squared minus the inner radius squared. Let's look at one more example. Okay, this example, what I'm going to do is use the region bounded by y equal to the square root of x, y equal to the square root of x, and y equal to x cubed, which is going to look like this. Now these two functions intersect at the point 1, 1 and 0, 0. So we have a region that's in between those two functions. And what I want to do is I'm just going to set up the two integrals. I'm going to assume you can do the actual integration. I'm just going to set up the two integrals, and what we're going to do is actually set this problem up two ways. First, we're going to rotate this about the x-axis, and secondly, then what we're going to do is rotate this about the y-axis. Now, if I rotate this about the x-axis, what I'm going to get is, again, a picture that looks a bit like this one. Okay, and if we look at a sample slice of this, what I'm going to have is what we can see, or I hope you can see, is that what we're going to have is definitely a washer. We've got holes in the center of these, and let's put a couple of them in here so you can see them. Right? So what we have are washers, and again, what I want you to realize is that these washers are stacking in the x direction. It's like we're sliding them onto the x-axis. And what that means is our integral is going to be in terms of x. So whichever way you're stacking these discs or washers, that's the variable of integration. So what I want to do then is we're going to set this problem up in terms of x's. So I'm going to get an integral in terms of x's. So keep that in mind at all times here. Now if we look, our washers in this case are going to start back here at 0. The final washer is out at 1, so I'm going to integrate from 0 to 1. We do need our pi. We're going to do the outer radius squared minus the inner radius squared. So outer minus inner. So remember, the volume of the big disk minus the volume of the hole. Okay, now if I look at each of these, if I look at this one right here, the outer radius goes from the x-axis up to this function right here. And what was that function that's up there? That topmost function is y equal to the square root of x. So our outer radius is given by the square root of x. Our inner radii is this function that's right here. And that function was y equal to x cubed. So our inner radius is going to be given by x cubed. And so our integral then we really want to do is pi. We're integrating from 0 to 1. The square root of x squared is x minus x cubed squared, which is x to the 6th dx. And as I said, I think you can finish that integral on your own, but I will let you know what the answer is. So when you do this integral, you should end up with a final answer of 5/14 times pi. Okay, now let's take that same example, that same picture, and instead let's rotate it around the y-axis. Okay, so again, we're going to use y equal to the square root of x. We're going to use y equal to x cubed. That's this picture, that's this function right here. And again, they still intersect at 0, 0, and 1, 1. This time we're going to spin this around the y-axis. So what we're going to get is we're going to get a picture that looks like this one. And again, I think if you can see, if we put a sample disc in here, it is actually a washer. We have a hole in the center. Put a couple in here. There's another one. Okay, so what we're going to have then is a picture that looks like this one. So what we have is kind of a bowl on the outside and rounded edges in the center of our bowl. But okay, so let's see. Now again, what I want you to realize that when we stack these washers, we are stacking them in the y direction. So if so in the first case we were going around the x-axis, now we're going around the y-axis, and so our integral in this case is going to be with respect to y, because we are stacking these along the y-axis. If you look, they are stacked vertically, and so again I want to integrate this with respect to y. Now if we look at our y values, our disc washers actually start down here at 0. They end up at the topmost washer is up there at 1. So what I'm going to have is I am still integrating from 0 to 1. We are going to have an outer radius squared minus our inner radius squared, same idea that we had before. They just might not be exactly the same functions. Now again, keeping in mind that we are integrating with respect to y. So we look at our two functions. We had y equal to the square root of x, and if we had y equal to the square root of x, if we solve that for x, what we really have is x is equal to y squared. And we had the other function that we had was we had y equal to x cubed, and if we solve for x, we're going to have x is equal to the cube root of y. So kind of keep in mind when we're integrating with respect to y, remember our functions need to be in terms of y in our integral. Now what we need to do is just identify which of these is the outer radius and which of these is the inner radius. Well, if I look at this washer right here, what we can see, what I hope you can see, is that our outer radius is right here. It goes from the axis out to this function right here, and I hope you can remember that that function is the function where y was equal to x cubed. Well, if y was equal to x cubed, x is equal to the cube root of y, and so our outer radius is given by the function cube root of y. Our inner radius then is given by this inside piece in this case, inside function, and that function again is, that was originally y equal to the square root of x, but again, if we solve that for x, we got x equal to y squared. So what we're going to have here is our inner radius is y squared. And that should complete the setup for this. If we write this a little neater, we're going to get pi, the integral from 0 to 1. If we square the cube root of y, I'm going to get y to the 2/3 power, minus, if we square y squared, we're going to get y to the 4th power dy. So what we're going to end up with is pi, integral from 0 to 1, y to the 2/3 power minus y to the 4th power. If you can go ahead and do that integral on your own, but you should end up with an answer of 2/5 pi. Now what I want you to realize, and I want you to notice that in this final example, is that the volume you got by rotating this region around the x-axis is not the same as the volume we got by rotating it around the y-axis. They are different shapes. They look similar, but the one is a little flatter and a little wider, and the other one's a little more narrow, and they do actually have different volumes. So it's very important that you remember which axis you are rotating your regions about, and so you draw an appropriate picture. Pictures are really important. Step 1 to all of these problems should be to draw a picture. Okay, that concludes this lesson on finding the volumes of solids of revolution using discs or washers. Good luck!